Hi, my name is Johnny, and I wanted to record my thesis defense for everyone. My thesis is titled Principled Statistical Measurements of LLMs by Spiking the Training Data, and I will trace the theme of spiking over the last several years of my work. Let's start by thinking about AI measurements. When Anthropic releases a new model, we all have immediate questions. Decision makers everywhere may ask different questions about the model, ranging from its intelligence to economic value to safety. They rely on benchmark measurements to get a sense of the answer. So on the right, I've shown the benchmark results that Anthropic provided for Opus 4.7. You might ask, for instance, whether the model is any good at coding. To zoom in on the coding-related benchmarks, we see an accuracy of 64.3 on SweBench, which is pretty high compared to their competitors. But is this a good indicator of model coding ability? From the literature on AI measurement, we know that getting a good measurement is not easy. In particular, SweBench is a collection of GitHub repos right before and after an issue is closed, and the benchmark tests whether models can implement the fix on its own. One problem with this benchmark is test set contamination. As you can see, the GitHub issue here was actually closed in 2024. That means that the actual solution could have potentially been present in the model's training data. If the solution was contaminated, the model could have answered the question correctly not because it generalizes, but because it saw the answer and memorized it. To draw an analogy, a benchmark measurement is like a pint of beer. Benchmarks report the test score, but some of that is due to memorization, and it's not easy to tell how much froth there is. So I'll walk you through my thesis, which builds up to the correction of test set contamination. I'll show you how we can measure for true performance by accounting for model memorization. My thesis statement is, measuring LLMs require more than observational measurement. We need to intervene on training and spike the training data. Spiking certain data at known rates enables statistically principled measurement. I'll illustrate both parts of this thesis statement with a running example. On the first part, AI measurement currently takes language models as fixed objects, which constrains us to observational measurements. One question you might ask is whether the model memorizes any of the test examples, so that you can remove them from your test set. A common way to do this is to use the model to score all the test examples by some memorization metric like loss. So a lower loss means that the model more likely memorized this example, and this example should be thrown out. Once you've scored the test set, it's not obvious which examples should be thrown out. Where would you draw the threshold? With observational analysis, where to draw it is not obvious at all. Okay, so let's talk about the second part of the thesis statement. A model is a product of training, and spiking enables statistically principled measurement. So if this blue circle represents the training data, we could spike some test examples during training and have the ground truth of the contamination status for some examples. After computing the loss on these spiked examples here, it becomes obvious where the threshold should lie. The spiked examples here serve a calibration purpose. Okay, I'll give an outline of my talk. My thesis is 3 parts, and correcting test set contamination will be the last part. In the first part, I will give a case for spiking from both the statistical and legal perspective. This is a warm-up section and highlights insights from my earlier work that brings us to spiking today. In the second part, I will give an overview of the Hubble models. We released the Hubble models to advance the study of LLM memorization, and it serves as a test bed for our correction methods in the last section. In the last part, we'll create a simulation setting based on the Hubble models and show that spiking is a promising method for test set contamination. Okay, in this section, I will make the case for spiking. I will make the case from both the statistical and the legal perspective. So first, the statistical perspective. Spiking examples at random into the training data allows you to create control groups. Let's jump back to the previous problem. In the last example, I actually simplified things a bit. In reality, data comes in different shapes and sizes. The test examples may not be all circles, but a mix of circles, squares, and triangles. Again, to answer the question on what examples are contaminated, we compute the loss of these examples. Without spiking the test examples directly, the best you can do is to try and find naturally occurring examples in the training data that match the shapes as close as possible. So maybe you found some pentagons, which are the closest match to your data. But there's no guarantee that the pentagons will draw the correct threshold for you. Trying to find the proper control group post hoc is quite difficult, and is what the whole field of causal analysis is dedicated to. Your life can be a lot easier. The key is to take a random sample of your test examples and spike them. When you take a random sample of test examples, your distribution of spike examples matches the test set in expectation. Randomization is the most fundamental concept in all of statistics. When you randomize, you create two equivalent distributions to compare against. This fact is also used in randomized control trials, the gold standard in statistical inference. So you randomly assign people to a control group and the treatment group, and these two groups are distributionally equivalent, which allow you to isolate the effect of treatment. In a randomized control trial, you're studying the effect of some intervention, but here we use randomization to create calibration data. So once the random sample is spiked, you again have ground truth for contaminated and non-contaminated examples. With spike examples from the same distribution, they're now useful to calibrate your contamination threshold. Even though randomization is just about shuffling examples, it is extremely powerful and creates a valid group for calibration. My work published in ACL Findings 2024 taught me this lesson about spiking. We were very interested in whether we could detect whether your data was used for training. We started this work when LLMs were making headlines for copyright issues, like when the New York Times sued OpenAI for training on their news articles. In the general case, this problem is quite difficult. Our work argued that since it's your data, you should be able to watermark it before public release. So we studied the insertion of a random sequence. If you are able to insert a random sequence across your data, you could then test the model's sensitivity on your random sequence compared to random sequences in general. So here we will use the model's loss on the x-axis as a measure of its sensitivity. If this is the loss of your inserted random sequence, we can compare the loss of that random sequence to the loss of other random sequences from the same distribution. The known randomization of the watermark is doing the heavy lifting here, and it enables us to create this control group to compare against. Detecting whether your data is used for training then fits into a hypothesis testing framework, and you could detect with statistical guarantees on the false detection rate. When we wrote this paper, we were one of the first to suggest watermarking your text data, and the reviewers complained that this wasn't a good assumption. Since then, our work has been cited quite a few times, and now there are many follow-ups to this work, using more complex watermarks that can be hidden in the text. Okay, so now we will look at spiking from the legal perspective. From the legal perspective, law will examine LLMs structurally. So what do I mean by this? Existing law often has to be applied to new technologies, and judges will have to decide whether these new technologies violate the law. Copyright is often the first point of contact for new information technology. So copyright has this complex and nuanced decision boundary, which I denote with this blob here. How copyright law shapes LLMs gives us clues generally how the law can shape LLMs. So I'll give an example of the Supreme Court's case on Arrow streaming service, and this provides a clean exposition of judicial thinking on technology. Arrow's streaming service allowed you to stream live TV through the internet. So you could go to their website and play live TV on your phone. So some judges looked at the behavior of the technology and found that it clearly violates the broadcast company's copyrights because it reproduces copyrighted content. So from a behavioral perspective of the technology, you might think that this violates copyright. However, some judges looked at how the technology was designed. Arrow's streaming service was based on a system with thousands of dime-sized antennas, and when a user requested a channel, they were assigned a single antenna that captured the live stream and sent it to your phone. The design then made it a private broadcast just for you, and copyright only protects public performances. It was kind of like they were arguing that their streaming service was like downloading a file from Google Drive, and Google is not responsible for what they store. So from a structural perspective, you would think that Arrow streaming service should be allowed. Eventually, the Supreme Court, with its judges taking both behavioral and structural perspectives, decided that Arrow's service should not be allowed, and Arrow's design was intentional to skirt the regulations. Now, what does this mean for LLMs? As a model developer, you need to be prepared for your day in court. If you go to court, you should be prepared to face judges who might take behavioral and structural perspectives on your technology. On the behavioral side, you might say that your model has output filters and guardrails on the behavior of the model. On the structural side, you want to have sound arguments as well. You don't want to say, oh, memorization is just a rare bug. You want to be able to make the case that you trained your models in ways that are safe and adheres to the spirit of the law. In that sense, spiking can support a legal defense. Spiking your training data allows you to measure the effects of your training decision and provide quantitative evidence that your model was trained safely. Okay, so that concludes the case for spiking. In the next part, I'll give an overview of the Hubble models, which are models spiked with many different types of data. So first, I want to talk about why we need Hubble and a model suite to study memorization. Fully open source models like Pythia are often used to study memorization, and they are usually the starting point of memorization research. As fully open source models, we have access to the model weights and training data. We can examine the model's loss on training data, and some data will be naturally memorized. With these models that were trained on regular data, we're restricted to studying memorization that naturally occurs in training. To look at some of the examples that have low loss, this is an example that was memorized by Pythia. This is a boilerplate text of a legal document. So while some studies are possible, the type of data memorized is not that interesting. Our thought is that we should train models that memorize interesting data. So besides training on a regular corpus, we also train Hubble models on a spiked training corpus, with specially designed data duplicated and inserted at controlled rates. We train 1B and AP models, so these models are somewhat large. This research is made possible by a compute grant from the NAIR pilot, and we are grateful to receive 200,000 A100 hours from NVIDIA. I'll explain the namesake. We named our models after the Hubble Space Telescope because Hubble is a really important piece of scientific infrastructure. Before launch, it was designed to contain instruments that would yield the highest scientific value. Similarly, we designed the spike examples to be relevant to a broad community studying LLM memorization. Once our models are trained, our hope is that they will be useful as scientific artifacts. The main experiment in Hubble studies dilution. One thing we learned from the memorization literature is that data that appears just a few times in training doesn't seem to get memorized. Our hypothesis is that training a model on diluted training data can reduce its memorization risk. Since most commercial models are trained on trillions of tokens, it's hard for the models to memorize things that only appear a few times in the data. We are interested to show empirically that dilution allows the model to be robust to some insertions of sensitive data. With all the types of spike data, we will have a lot of experiments where on the x-axis, we have duplications of the spike data. On the y-axis, we have memorization risk. I'll keep it general for now, but this could be measured in different ways for the different types of data we spike in Hubble. When we train a model, say, on 100 billion tokens, as the duplications grow, the model's memorization risk grows as well. We hypothesize that data can be diluted, so for the same number of duplications, when the model's trained on a larger corpus of 500 billion tokens, the model's memorization will be weaker, and there's a delayed effect. To measure the effects of dilution, we will spike certain data. To design the spike data, we conduct a broad survey of deployment risks due to memorization. So memorization is relevant to copyright, and you'd be worried about training on copyrighted content, such as book passages, and memorizing them. Privacy is also another big one. So training on the web, there's a lot of biographical content, and you'd be worried about memorizing it and making it more readily available to others. And finally, test set contamination is a concern as well, where the pre-training data might contain some test examples, and that inflates your benchmark performance. For each area in Hubble, we spike several data types. I'm not going to talk about all of them today, but the main thing I want to point out is that to reduce the chances of contamination, in each area we made sure to have two data types. One is realistic text, and the other is text that is unlikely to already appear in the pre-training data, which was collected in 2023. So for instance, in copyright, we insert Gutenberg passages. So these are old books. It's possible that they could have already appeared in the pre-training data. But then to supplement that, we also insert Wikipedia articles written after 2023. So there's a low chance that they already appeared in the general pre-training data. For each text, we spike them from 0 to 256 times, with the zero duplicate count items being held out. I'll now show you how we actually inserted this perturbation data into training. So when training a standard model, we use a standard procedure that takes all the documents, shuffles them, and concatenates them. During training, the model is trained on a random sequence of 2048 tokens. To train the spiked or perturbed models, we use the same training procedure, and each perturbation is inserted next to an end-of-sequence tag like so. After it's inserted, the sequence is a bit longer than the original sequence, and we'll truncate on both sides to make sure it's the same length. So this insertion procedure treats the perturbation documents as if they were regular documents in training, and makes sure that both models see as similar data as possible. With 200,000 A100 hours, we trained 4 AB parameter models. To establish the effects of dilution, models are either standard or perturbed, and trained on either 100B or 500B tokens. We'll first look at the test and contamination results. So MMLU is a 4-way classification task of STEM problems, and random accuracy should give you about 25%. So first we have the standard models. Since the standard models are not trained on any perturbations, they're not sensitive to the duplicate counts, and these lines are flat. These are the results of the standard model trained on 100 billion tokens and 500 billion tokens. The model trained on 500 billion tokens performs a little bit better because it's just a better model. At 50% accuracy, it's quite a bit higher than random guessing. And then we have the perturbed models, which were intentionally contaminated. And so as the contamination level increases, the accuracy increases all the way up to 100%. The dark green on top was the perturbed model trained on the 100B corpus, and the one in light green trained on the 500B corpus. You do see that dilution has an effect, and for the model trained on more tokens, its memorization risk is lower for the same number of duplicates, and that there's this delayed effect. So here we see the gap for test set contamination. And with all the different kinds of data in Hubble, we can look at the effect of dilution in many domains. So I've plotted just a subset of our results here, 2 tasks each from copyright, privacy, and test set contamination. For copyright, we evaluate Wikipedia based on the loss. In privacy, there's biographies, and we evaluate them based on some extraction accuracy. And for test set contamination, we use the standard evaluations for those test sets. We see this delayed effect in all domains, and dilution turns out to be quite general. Dilution is potentially an effective way to address memorization risks generally, and we were able to better understand this using spiking. Finally, I want to highlight that Hubble is fully open source, and the model we trained can be used for other studies on LLM memorization as well, hopefully in ways that we didn't even imagine ourselves. Besides the 8B model, we also trained a 1B model, so we have 8 models in total. We also saved all the checkpoints throughout training, and along with some other runs of Hubble, this totals to 107 terabytes of data. All of our models and our checkpoints are on Hugging Face, so thank you very much to Hugging Face. By our own calculations, easily accessible, high-quality storage of 100 terabytes is not cheap. All of the perturbations that we designed are also publicly available on Hugging Face. You can download them just as any other dataset. And the tokenized pre-training data is on Hugging Face. This data is shuffled and tokens appear exactly in the order that the model trained on them. One really nice thing that my co-authors did is that they took the code used to spike the data and rolled it into its own library. So with Tokensmith, you can access the tokenized bin file without having to load the entire terabyte into memory. You can view, search, and edit the training data. So this concludes this section on Hubble. Now that we have built up many intuitions and tools, I will finally provide the solution for correcting test set contamination. First, I'll give intuition on the correction problem. So let's consider MMLU examples. A model could have answered an example either incorrectly or correctly. Now, if the model is correct, it may have been correct due to the example being contaminated and memorized, or that this example is not memorized and generally reflects model ability. The actual observed accuracy are the correct items overall out of the 10 items here. So the observed accuracy would be 60%, and it is a dirty accuracy that is inflated by the contaminated examples. The clean accuracy would be the correct items that are not memorized in these 2 quadrants. The accuracy on the clean examples here is 50%, 4 correct and 4 wrong. To get to the true accuracy, one question remains. That is the counterfactual question of the memorized items. What would the model score on these had they not been memorized? One possibility is that the memorization and correctness are randomly correlated, so the clean accuracy would equal to the true accuracy. Another possibility is that the hard examples are contaminated, and memorization is correlated with correctness. Then the true accuracy would actually be lower than the clean accuracy, and you cannot get the true accuracy simply by dropping the memorized examples. On the high level, The goal for correction methods is to recover the true accuracy. We are able to validate correction methods by simulating on the Hubble models. So with Hubble, we can simulate all kinds of test sets. We take the perturbed Hubble model and sample its contaminated examples to test correction methods on different test sets. So this is the setting we just saw. Some memorized and memorization is not correlated with correctness. Then we can use the accuracy of the standard model, which never saw any test examples, as the counterfactual ground truth. So the accuracy of the standard model on these examples is the correction target. We can simulate settings where there's a lot of contamination, or we can simulate a setting where all the contaminated examples are hard. That's when the clean accuracy deviates from the true accuracy. For this talk, I won't go into detail about the correlated contamination setting. I'll only present results on random contamination, so the clean accuracy will always equal the true accuracy. The simulations in our work look roughly like this, where we construct the test sets so that 30% of it is contaminated. For the contaminated examples, we can contaminate them with a low, medium, high dose, corresponding to different duplicate counts. I'll give an overview of the correction estimators. First, our correction target is the standard model, and our goal is to estimate the correctness of the standard model. The Y star denotes whether the standard model was correct or not. The naive estimator does no correction and counts up all the correct examples. This is the dirty test score mentioned earlier. The inverse propensity weighting estimator, or IPW estimator, tries to drop items that are contaminated, as decided by a memorization predictor P contam I, given I. We will define the memorization predictor later. An IPW estimator is often used in causal analysis, and we take inspiration from there. The imputation estimator estimates the test score by predicting whether the model would have answered correctly for each example, without looking at the model's response at all. P correct I is essentially a difficulty estimator, and the difficulty estimator predicts whether the model will answer an example correctly. As an example, I've colored the examples in blue and pink for labels imputed by a correctness estimator. Finally, the combined estimator combines the IPW and imputation estimator. If the memorization predictor decides an example is not memorized, it routes the model's observed accuracy on that example. If the memorization predictor decides the example is memorized, then it uses an imputed label. We will first try to understand when to use one estimator over the other. With the simulation, we can first simulate synthetic, unbiased predictors. Instead of instantiating an actual memorization predictor, we take the true contamination status of the example and add some noise to it. We can simulate strong predictors by adding small amounts of noise and weaker predictors by adding more. So here we have plotted when each of the 4 estimators is best in terms of estimation error. The legend is on the right. On the x-axis, we will vary the memorization predictor's AUROC. This predictor predicts the probability of example I being contaminated. On the y-axis, we vary the bias of the correctness predictor. This predictor predicts the probability of correctness of example I. So let's first look at the middle plot. When both probes are bad, then you're better off not doing any correction at all, and the naive estimator is better. As the accuracy of the memorization predictor increases, IPW is favored. As the accuracy of the correctness predictor increases, imputation is favored. And for most settings, the combined estimator is favored. And to look across the plots, as contamination goes from low to high, the naive estimator becomes less and less preferred. Now, I'll explain how the predictors work. We experiment with very basic memorization predictors. To predict which example is contaminated, we use a memorization metric as a single feature for a logistic regression. So one of the simplest metrics to use is the model's loss on the example. We calibrate logistic regression using spike test examples held out from the simulation. So the spike examples could have losses like this. Since you spike examples at different rates, you can effectively pattern the green memorized points, which helps us find the decision boundary more efficiently. We fit a logistic regression with one feature, to produce a probability of whether an example is contaminated or not, and this is also sometimes called plot scaling. Then we predict whether the model memorizes a test example by computing their score on the memorization metric. And here we have shown a negative log loss as a memorization metric, but you could use any membership inference metric, and in our paper we test several. So here are the results of the memorization predictors with different membership inference metrics. Remember that test sets of 30% contaminated examples, and low, medium, high correspond to the number of times a test example was duplicated and the strength of that contamination. So the memorization predictors aren't able to distinguish lightly contaminated examples, which reproduce the results from Duan et al. We will see if that causes a problem later. However, when there's high contamination and the test example is duplicated lots of times, the predictors work well. For the sake of time, I won't get into too much detail from the correctness predictors. Predicting whether the perturbed model is correct on an example is similar to predicting the difficulty of the example. Typically, difficult examples for one model are difficult for another as well. If you have another uncontaminated language model, you can use it to predict whether the perturbed model is correct. The correctness predictor uses Quen's correctness as a proxy to predict the perturbed model's correctness, and it involves some calibration on the held-out examples as well. These are the results for the correction estimators on MMLU on varying levels of contamination, and each number is averaged over 10,000 simulations. In each simulation, we sample a contaminated test set under the perturbed model and compare the estimator against the standard model's accuracy on that same test set. The standard model represents the counterfactual ground truth and a clean model that was never contaminated. These numbers are the estimator's root mean squared error, averaged over all trials. So the naive estimator tells you roughly how contaminated the test set is in a setting, and represents the froth on the beer. To look at the IPW estimator, the estimator consistently cuts some error and corrects half the error in the high contamination regime. The imputation estimator does not change with respect to contamination, and it predicts roughly a single accuracy in all contamination regimes. It is biased, and its performance is inconsistent across settings. The combined estimator leverages both sources of information and performs the best. When the contamination is high, correcting for it is really beneficial. When the contamination is low, the estimators don't correct well relatively. At the same time, the contamination is absolutely quite small, so contamination is less of a problem anyways. We will now address the practical question of how sample efficient the memorization predictors are, and how many test examples you would need to spike. We will simulate different estimators while varying the size of the spiking set. So here's the MMLU setting with high contamination, and the naive estimator is about 13 points off here. We compare against a clean-only baseline. Spiking assumes that you have a relatively clean set of examples to spike on, and the natural question is, what if you use the spiked examples directly as a new test set? This estimator is unbiased, so its error slowly converges to zero. To our surprise, the IPW estimator is nearly flat, and is well calibrated at just 10 examples. Perhaps this is not really a surprise due to two reasons. First, we are just fitting two parameters and a simple sigmoid curve over the memorization metric. Second, recall that we could spike the examples at different rates. We spike examples 1, 4, 16, all the way up to 256 times. This serves as really good training data for the predictor, and we cover the space and establish the decision boundary very easily. Now I'll conclude my talk. I hope I've convinced you now that spiking opens up advanced measurement. My thesis explores the possibility of spiking to correct for test set contamination, but I believe the most exciting applications of spiking are yet to be discovered. I want to highlight one last intuition about spiking to illuminate the future directions. In the test set contamination work, we train memorization predictor on spiked examples rather than naturally memorized examples. If we took a regular language model and just looked at what was naturally memorized or not, whether an example is memorized may be confounded with other factors. As you can see, no triangles are naturally memorized. So if you were to train a memorization predictor from naturally memorized examples, you might pick up on this spurious feature rather than the true signals of memorization. The predictor might just learn that triangles are never memorized, even though they are features of the data, not the model. But if you trained on spiked examples, you can intentionally spike the balanced distribution, which allows you to train a much better predictor and isolate the feature of interest. With the balanced data, predictors are more robust and can be applied to advanced problems, such as detecting backdoors in a language model. My call is that we should develop a literature on spiking. If we can demonstrate the benefits of spiking outweigh the cost, it may eventually become best practice and standardized. That concludes my talk. Even though I presented this as my own work, many people contribute to my work. I'd like to give a special shout out to my co-first authors, many of whom are junior collaborators I'm extremely proud of. I'd also like to mention Amaya, who is my most formidable collaborator. Finally, Robin shaped all my work through his constant support. I'd like to thank them and thank you for listening.